want to go? Okay, never mind. Okay. If there's no questions, we'll finally get going tonight. Okay, we finished chapter 5. And I know some of you are working on the chapter 5 test because I've had a couple of questions today about it. That's good to hear. And we're continuing with chapter 8. Chapter 8 is work and energy. You may ask yourself, why did they put those two in the same chapter? They're manifestations of the same thing, work and energy. Okay? So that's why they are located together. Now, it won't advance PowerPoint until I click on the screen, and then it'll advance. Okay, let's first talk about what work is. Okay, now, let me ask this question. Do all of you have books? Yes or no? Yes for Macy. How about it, Manasseh? Yes, I remember seeing you with one. Mercy? Excellent. Molly? Molly, you got a book? No, you don't. Okay, well, I'll try to write down things for the book. Now, since this first slide that they show here is pages away, let me go back to the screen sharing and do a new share, and this time we'll do the whiteboard. Now, my question to you here is, do you mind my writing on the board with my pad? Yuck. You can't see it. The taskbar is continually moving, trying to move down. Okay, stayed up there that time. Or would you rather I type it in the text? It's up to you. I'll do whichever you prefer. Do you have a preference? Some of the things I think might do a little bit better with typing. So I'll do that, but then when not, I will go to writing on the keypad. All right. Get the book in front of me so you can hear me better. I'm less and less pleased with this HP that they gave me from work. What is work? That's how 8.1 is on work. What in the world is work? The common idea is different from the technical idea, and we'll talk about examples of that. And work can go one of two directions. It may be that I lift the book. I'm doing work on the book, changing a form of its energy. However, I dropped the book on my lap. It wasn't hard, but I could feel it. It did work on me. Okay, so an object can be, you can do work on an object, or it can be do work, in the opposite direction. So work kind of involves both directions there. Okay. The technical meaning of work requires that work must be done by one object on another object. Okay. For instance, and they do give a picture. I'm going to show this picture. Not going to do this often, but here is an example. Now, I know my voice will go out, but here's an example. Here, the people are trying to do work on a crate, something like that. Here, the hammer is doing work on the whatever it is, nail or thing that's being driven into the ground or into whatever it's being given. Work is one object doing something to another object. Okay, now let's go back to that first one. In the first one, the guy is struggling against the crate, and guess what? He's not moving the crate. It's either too heavy, too much friction, or something else like that. Can you hear me? Okay. In that case, the guy's not doing work. No matter how much force he's exerting, no matter how much he's pushing or pulling, he's not doing any work on the crate. The second guy there is moving the crate, therefore he's doing work on the crate. So there is a concept that's important with work. So I think I'll start with text here, and this will be the first text, okay? The physical definition of work is even more narrow than what we've just been talking about. Here it is. Work is the product of the force in the direction, whoops, ooh, that's, I don't really care for this keyboard either. Sometimes it's so sensitive that you even get close to it and it types, and other times it seems like you can bang on it and it doesn't work, okay? The product of the force in the direction of the motion and the magnitude of the displacement. Okay, big, long, hairy definition, okay? Let me expand it a little bit here so it doesn't take up so much room in that one dimension. Okay, so work is the product of a force in the direction of the motion and the magnitude of the displacement. Now, that's a little wordy, and with all those prepositional phrases in there, it's not real clear what goes with what. Let me tell you, talking about a product is a multiplication of a couple of things. The force, but not the whole force, is the force in the direction of the motion. That's the first product, the factor in the product. The second is the magnitude of the displacement. That's what the work is. Now, why, whoops, here's somebody else trying to get in, and look at there, that box is still showing up, even though I didn't go to full screen. So, but at least it's down here at the bottom. Hopefully it won't be in the way. That student that told me that today, don't know what happened. Now, because it was blocking, you can't see it, but it was blocking my view of who it was. Let me, okay, I see that Mika is here now. Okay, Mika is here. I think we got everybody else already accounted for. And Jalen, you're still the odd man out, you know, all M's except you. Okay. So I'm going to close off this if I can get it to close. There we go. That's a box in the middle that is blocking my view of what the screen is. Okay. Now, so why did they say magnitude rather than displacement? They said the force, product of the force, in the direction of the motion and the magnitude of the displacement. Well, here's why. Force is a vector quantity. It has a direction. Displacement is a vector quantity. It has a direction. Work, the product of those two, we haven't even talked about how to multiply vectors, but guess what? We don't need to talk about that because you're only dealing with magnitudes. Only the portion of the force in the direction of the motion and the magnitude of the displacement. Now, I don't usually do this, but I think it might work in this case. So I'm going to do it. I mean, I would do it if we were in class. Let's try it here. Okay. I don't know if you can see my chair here. Maybe just the very top of it. Okay, right? Okay, and you see me behind the chair. I'm going to pull on the chair. Now notice my arm. You can't see it too well. Maybe turn it this way. Okay. Yeah. See the back of the chair here, and here's my arm. My force is being pulled in the direction of my arm, but the chair is moving only in a horizontal direction. I'm not lifting the chair. I'm only pulling here. So what that means by the product of the force in the direction of motion, remember forces are vector quantities. This is the vector coming up my arm here. There is a component of that in the horizontal direction, and there's a component in the vertical direction. The vertical direction is not doing any work because I'm not lifting the chair. However, the horizontal component, the component in the direction of motion, that component is doing work on the chair. Okay? Now, if this were a fixed chair, I could move another chair over here. This one's a roller. And if that other chair was really heavy and I pulled with the same force but didn't move it, even though I exert the same force, if there is no displacement, there is no work. Because work is the product of the force in the direction of motion, not just the force, but in the direction of the motion and the magnitude of the displacement. Okay? Now, here's the formula for that. I think I'll do that in a separate box here. Okay? And here is your formula. Capital W stands for work. Okay? Work is equal to, and I'm just going to put F, and they like to use the symbol S. I kind of like D, but since the book is doing this, we'll go with that. Well, what is work? What is W? W is the work. Wait. Okay. F is the force applied in the direction of the motion. Okay. And what is S? S is the magnitude of the displacement. Okay. Let's stretch this out a little bit so it makes maybe a little more sense. Okay. There. The formula for work, W equal F times S. F is actually the magnitude of the force in the direction of your displacement, of the motion, and S is the magnitude of the displacement. Why do we keep saying magnitude? Work is not a vector quantity. Work is a scalar quantity. Force is a vector, displacement is a vector, but we're dealing with their magnitudes. Okay? Now, what are the units for it? Well, the unit for force, let's see, I think I'll do this. Nope, I won't. Oh, there it is. Yeah. Okay. 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 Force is measured. These are the units. I'm going to put them in parentheses. Does anyone recall what the unit for force is? Especially in the SI system, sort of meaning the metric system. What's the unit for force? Named after good old Isaac? Newton, of course. Now, what's your typical SI unit for displacement? I said SI, another name for what system? Metric system. Metric comes from the word meter. So that's your displacement unit. So force times displacement would be a Newton times a meter. Well, a Newton times a meter has a special name. And that special name, I'll put it back in parentheses because it's a unit, is a joule. Okay? Named after James Prescott Joule. That's why it's capitalized. Newton's named after Newton. Meter's not named after anybody, so that's a lowercase. A Newton meter is a joule. Now, broken down into the fundamental units, what does that mean? Okay? So in the fundamental units, a Newton is a kilogram, not named after anyone, meter per second squared. I can't do a squared here, so I'm going to do a caret 2, that means second squared. That's what a Newton is. And then multiplied by another meter, okay? Now, that's an awkward way to do it, so let me clean that up just a little bit. That would be a kilogram meter squared. So the meter squared is also squared now. The meter is also squared, and then that's divided by your second squared. Okay. A kilogram meter squared per second squared. Those are the fundamental units that make up a Newton meter or a joule. That's what we have for work. That's how we measure work. Kilogram meter squared per second squared. Those are the fundamental units, or Newton meter, or even simpler, joule. Okay, those are the units for work. Okay, so 1 Newton meter is 1 joule. Now, how about the U.S. customary system? I really didn't leave room there, so let's do it down here. What is U.S. customary unit for work? What's your unit for force in U.S. customary system? You read it when you step on the scales. Pounds, okay? And what's your U.S. customary unit for distance? You walk on them. Foot, okay, exactly, FT. So the unit is the force times displacement would be pounds times feet, but most of the time we say that not pounds feet, but foot pounds, okay? That's how we usually say work in the U.S. customary system, foot pounds. We don't usually break that down into anything smaller because a pound, if you broke it down into something smaller, it would be a slug foot per second squared, and then that would then be a slug. I don't know why this went down there. Let me select and go back to this box. I had no intention there. I don't know why that went there on its own. Okay. All right. So I don't usually go any lower than that. If you did, it would be slug foot squared per second squared. I don't like to go there, so unless the book makes me, I won't go there. So in terms of force times displacement, it's pounds times feet, but we usually reverse that and call it foot pounds. Okay. Now, so the U.S. unit of work is the foot pound. Now, and again, what I've already talked about, work is not a vector quantity. Okay, it is a scalar quantity. It has no direction associated with it. Okay, forces, yes, displacements, yes, but not work. Now they have a little blurb off to the right of those definitions. James Prescott Joule, interesting character, a physicist born in England. He showed a lot of the early experiments that related that heat, energy, work are all interchangeable. And they named that unit work joule after James Prescott Joule. So we're ready for example 1. Okay. Now, I'm going to show you the picture first. I know when I show you the picture, sometimes my voice goes out. I don't know if you can hear me, but there's a picture. A guy has picked up off the ground a toolbox, it looks like, or something like that, and has put it up on his shoulder. Did he do any work? Let me show you again. He picked it up off the ground and put it up on his shoulder. Did he do any work? Yes. He exerted a force, the lifting force, overcome gravity, and moved at a distance. Okay. That is doing work. If that had been a very, very, very heavy crate, and he tried to do this and couldn't lift it, and he strained and grunted and sweated and did all sorts of stuff, was he doing any work? If he couldn't lift it, if he didn't displace it, no, because work is force times displacement. No matter how much work he did, if he had no displacement, there's no work. But this time he did. Okay? Now, I need to get, okay. Yeah, okay. Here is example 1 then. Find the amount of work, so we're looking for work, and that's the unknown here, okay? Find the amount of work done by the worker lifting a 225 newtons of bricks. Oh, that's a bundle of bricks. I thought it was a toolbox. A bundle of bricks. So what does pound measure? Newton measure. 225 newtons of bricks. What's that a measure of? 225 newtons. That's the force due to weight. Now, I can't do a subscript of this, so I'll just do FW. That means force due to weight. And that force due to weight is 225 newtons. Okay? That was how he had to exert to lift those block bricks up onto his shoulder. I don't usually carry bricks on my shoulder. Okay? He lifted it a height of about 1.75 meters. What does that represent? That's a distance. What symbol are we using for distance? Displacement? S. That was your S. So S is equal to 1.75 meters. Unit, SI unit, meter. Okay. Now, catch this, folks. Remember, a meter is about the distance from one ear to the tip of the opposite finger. Okay? It's a little more than a yard. A yard is about from your nose to the tip of your finger. This is a little bit longer, about 3 inches or so longer. So it's about a yard. Now, a yard is 3 feet. This guy could have been pretty close to 6 feet tall, but he's not lifting it on top of his head. He's lifting it to his shoulder. So that would be close to 2 meters, but probably not. That sounds to be about right, 1.75 meters. Okay, the question is, how much work did he do? So let's go back up to this formula. And what is work again? Is formula force, and this will be the force due to weight. You don't have to put that in, but you're absolutely right, times S. Okay, and we know both of those. The force, the weight is 225 newtons. Oops, I usually put a space. Okay, times. Okay, now I'm going to put an X mark there. That's not an X, that's a times. And then what is the displacement? 1.75 meters. Okay, now my box is too small. Let me extend it out here. And that's equal to, pull out your handy dandy calculators. I'm using my cell phone. Okay. Calculator mode. Nothing special here, just pretty simple. 225 newtons times 1.75 meters equals what? Okay, 393.75. Now that's what my calculator read too. And what unit would that be? Absolutely. Okay. I don't know where there it went. Joules. Okay. Now, what's the only little thing wrong with that picture? Hey, why did you say that? Why? You got it. Bingo. Oh, well, you can't say bingo in Alabama. Whatever. Okay, 3 significant digits input here, 3 significant digits input here. You can't get 5 digits out of 3. So you count 3 digits, 1, 2, 3. Look to the right. That's greater than 5. So we say that is, and this sounds silly to do. I think I'll put it this way. That's approximately 394 because you're rounding up joules. Okay. So that's the answer they're looking for. That's the answer they want. And that is considered to be the correct answer, 394 joules. You can't get more precision out of a problem than you put into it. You put in 3 digits, you can only get 3 digits out. Okay? And that's what the book does. All right. Now, it looks like the worker carried those bricks over to a cart. And this will be example 2 now. This worker is pushing a 350-pound cart a distance of 30 feet by exerting a constant force of 40 pounds, blah, blah, blah. Well, now we're out of Canada and we're back in the U.S. again because we're using U.S. customary now. So a worker pushes a 350-pound cart. So what is that going to be a measure of? 350 pounds. What does pounds measure? Weight. And weight is a force. So that's going to be your force due to weight. I can't make it a subscript, so I just make it FW. And that is, what did I say, 350 pounds? Okay, that's the weight of the cart. Now, I was going to draw the picture, but I think I'll just show you the picture. Can you hear me talk underneath the book? Okay, there he is. Where is the weight heading? Weight is a force. It would be, has to have a vector. Which direction would that vector be in? The weight. What's creating the weight? What's the force that's creating weight? Okay, yes, and what is giving them weight? The gravity. Which way does gravity pull? Downward. You're absolutely right. I think I will try to draw a picture. So here goes my poor attempt at drawing a picture. Okay. All right. Here's the worker, not nearly as good a looking worker as that one. He's a stick man. Okay. This poor old stick man here has an arm coming this way and another arm coming this way. And poor old stick man here, he's pushing, so he has 2 legs. Boy, not very well proportioned, is he? Okay, he's pushing on the cart. Okay, so let's just say here's the cart. Ooh, that's not right. Okay, this is going down here. This is ugly. Yuck, really ugly. Okay, and here's the cart down here with all those bricks on it. But it's got wheels, and these are not very pretty wheels. They don't look like they wouldn't turn at all, do they? Okay, go here, and so there's the cart there. All the bricks are piled up on the cart, so I'm not going to do it. Blocks, whatever they happen to be, they're all over on the cart. Now the weight is gravity pulling downward, straight down. That's supposed to be straight down. I could make it better than that by using my straight line here. And the weight is straight down. Okay, supposedly straight down. It's not quite straight. Let me erase my ugly line here that didn't do where I wanted it to. Okay. Now, in fact, I shouldn't have done that. I should have done an arrow. So the weight is down this way. That's a better representation. It should be straight down, but I didn't quite get it there, but close. Okay. All right. And this is the force due to weight. Do I want it to? Yeah, let me type that in. This is the F sub W, and that's your 350 pounds. Okay. You might say, why am I doing all this? There's a reason. Okay. Actually, that wheel looks more like a block than it does a wheel. Never mind. Don't make fun of my drawing. Okay. Okay. How does he do it? Oh, he moves it a total of 50 feet. No, 30 feet. So he started here. Oops. I need my straight line again. So he started here. Why is it? Oh, okay. Okay. This happens sometimes, and I don't know how to undo it. Let me try this. I hope I don't lose it. No. Okay. I haven't figured out how to get it, so I'm going to stop that. I sort of messed up now. Okay. Because I can't get it to do what I want it to do. I know there's a way to do it, but I can't remember how to get it to change. Ah, that may have worked. Yes, it did. Double click. Remind me of that later. Okay. Now this isn't going to be as pretty, but it's going from there to over here, and that's not nearly long enough, but it's all I've got because I don't have any more room. So this is going to be 30 feet. That's the symbol for feet. It's a lot easier to write than FT. Okay, that's 30 feet in horizontal direction. Is this force doing any work in that displacement? No, because this force is downward. That displacement is to the left. A downward force does no work on a horizontal displacement. So that's not the force that's doing any work. What force is? We'll read the rest of the problem. By exerting a constant force of 40 pounds in the direction of the motion. Here's where the force that does the work is, the force that moves in this direction. His displacement's in this direction, so is the force. This force is I'm going to call this his applied force. You don't have to give it a thing, but I'm going to call it applied force. And this applied force is equal to 40 pounds, a constant applied force of 40 pounds. Okay, and he's able to move it with that force. So this is the force that's moving in the direction of the displacement, not the weight. The weight is always toward the center of the earth, and the crate is not going to the center of the earth. It's moving in a horizontal direction 30 feet that way. So now this is immaterial in the problem now. Up here, that was important. The weight was what he was lifting. The movement was upward. He was working against gravity. Here, he's not. He is pushing that way. Now, later we'll find out there is a component. Well, no, we probably won't. Don't sweat that. This is the one. Now, let me go back to my text here. Okay. This one is immaterial. What we have here is a displacement, which we've been calling S, or at least the book calls it S. Oops. Okay. S is equal to 30 feet to the right. Doesn't really matter. I can't type. 30 feet to the right. Okay. And the force that's in that direction is your applied force. So I'm just going to call it F. Okay. And that F is 40 pounds. That's the one that's doing work. The gravity force, the weight, is not doing any work at all. And so that's 40 pounds. Okay. So how much work is being done? What's the formula for work? W is equal to F times S. As long as the force is in the direction of the motion, this force, this pushing force, is in the direction of the motion. Okay, so this is equal to 40 pounds. I'll use the X sign again for times. 30 feet. Now I may have brought something up there, and let me see if I did. Okay. Let me go back and look at it. Yes, I did brought something up. The 350-pound cart, they didn't put a bar over that zero, but they did put a bar, and let's go on and do the math. Okay, we'll get back to it. Well, let's see, I should have done it here. Let me take that out. Okay, and what's that equal to? Whoops, let's put an equal sign in there. Well, 3 times 4 is 12, and you got 2 zeros, so it's 1200. What unit? Yeah, foot-pounds. Perfect. Okay, foot-pounds. Okay, let me expand my box here so I can get everything on the same line. Here's what I forgot to put down. The first one didn't have a bar. This one does. You shouldn't be going to bars, but okay. I'm going to try to draw here. Okay, and this is going to be ugly, so don't laugh. There's a bar on that zero, there's a bar on this zero. So we're multiplying 40 with a bar there times 30 with a bar there. How many significant digits does that mean? The bar means the zero is significant. 2 significant digits times 2 significant digits gives us 2. Count 1, 2. The 2 zeros are not significant, only the 12, 1 and 2. But you leave the zeros in there because 30 times 40, 30 times 40 is 1200. These zeros are not significant, only the 1 and the 2 are significant. So you can only get 2 significant digits out for 2 significant digits put in. So that should be 1200 feet, pounds, and that's exactly what they got. Good for them. Okay. Now, what I've already said, they mentioned on page 204, if you got a book, note that the cart weighs 350 pounds, but the applied force is 40 pounds. The weight of the object is a measure of gravitational pull by the Earth, not represent, and is represented by a vertical vector going downward. That's the one we put there. Therefore, the weight of the box is not the force to use to determine work, unless the guy was lifting that. Now, if he was lifting that thing, yeah, now he's doing work against gravity, so he is moving it upward. Then, however far he lifted, that would be the 350 being used there. This is a displacement in the horizontal direction, so it's only the force in the horizontal direction. Even though my figure doesn't look like it, this is going straight down. It doesn't have a horizontal component at all. Okay. Does that make sense? Now, excuse me. Let's go back to, I think this was the place. There it is. Here is a figure showing up. Now, sorry folks, we are going to have to introduce a little bit of trigonometry. Now, I know that none of you were required to have trig. Do any of you have any background in trigonometry? Little bit, okay? Anyone have absolutely no background in trigonometry? Okay, all of you have some, is that right? Or you're saying, yes, you do have no, whatever. So, okay, Jalen has none. Let me give you just what you need to know, okay? Here are some characteristics of trigonometry. And we're only going to be dealing with right angles here, okay? Right angles, angles that are 90 degrees, perfectly perpendicular to one another. When you have a right triangle like that, and you're pulling with a force up here, like I was pulling on the chair before, at an angle to the motion of the block. The motion of the block is this way. You're not going to lift that block unless it's awfully light up this way. You're only going to move it this way. So the component of this force in the horizontal direction is the only component that's doing any work. This vertical component here that they don't really show, that would be F sub y, because that's in the vertical direction. That does no work on the block unless you were also lifting the block when you pulled like that. We're assuming here, no, you're only moving the block. The displacement of the block is horizontal. So this is the only component. Now, here are the relations that we use in trigonometry. Okay? Here is the applied force, F. It's broken down into a horizontal component and a vertical component. They don't even show the vertical component here because it's not entering the problem at all. You're applying this force, so this is what you know. You don't know how much of that is horizontal, but here's the relationship. Okay? This is the angle in between the applied force and the component you're interested in. Okay? Now, I can't write on this screen, so I've got to go to the other screen to do it. I was starting to do that, but I realized, no, I don't have an ionizing pen anymore. I can't do that. So let me go back and keep that in mind. If I can get, let's go back to the whiteboard. Okay. And let's go on and clear this off. Can I clear this off without any repercussions? Okay, there it goes. All right, here are our trig relationships. Okay, this will be, oh wait, let me not do that. Let me try to draw straight lines. This will be a straight line. It may not be horizontal, but it'll be as close as I can get to horizontal. Okay, is that close enough for you? So this is your X component. So I'm just going to call it X. Whoa, that's not what I wanted to do. Well, it's not going to let me do that. I'll come back and label it later. Here is the applied force up here in this direction. Okay. Here is the, whoops, don't do that. Okay. Here is the vertical component we're really not concerned with. I hope that's sort of vertical. It's not quite. Here is your angle theta. Whoops. I shouldn't be doing that with a straight line. Okay. Erase that and erase this. Okay. Let me draw the angle. Here is the angle theta. Okay. And the theta looks like a circle with a horizontal slash through it. It's a Greek letter and doesn't really correspond to any of our letters too much. It's just the Greek letter theta. Now we call this the horizontal component, and to keep from writing the x, I'm just going, the f sub x, I'm just going to call it x. We'll call this the y, and we'll call this the f, because that's what the book calls it. Okay. Now, and by the way, this angle here, now this is how they represent a right angle. They do a little box here and make it perpendicular that way and perpendicular this way. That means it's a right angle, okay? My box isn't quite right, but you get the general idea. That is right angle to each other. Now, for this angle theta, we'll call x the adjacent side. So I'm going to give it another name. Oops, can't do it. forget that I'm in line mode. Okay, I need to be in letter mode. So we're also going to call this the adjacent side because it's part of that angle. It's touching the angle. The angle is this. This is we're going to call the opposite side. Now, there's a reason for me giving other letters to it. This we'll call, does anyone know what the long side of a right triangle is? Hypotenuse, exactly. Okay, so the F is now represents the hypotenuse. The X component is the adjacent side, and the Y, which we're not using, is called the opposite side. Here are your trig relationships. Trig functions are really just ratios. And here's what it is. We're not going to use a sine much, but here I'm going to give it to you anyway. The sine of any angle theta is merely the, that's supposed to be a theta. It's actually better looking one than that one. It's equal to the ratio of the opposite side over the hypotenuse. Is this ringing a bell with anyone who's had a little bit before? The cosine of the angle theta is equal to the adjacent side over the hypotenuse. Again, it's a ratio. And we will run into occasionally the tangent. The tangent of any angle theta is another ratio, as you might suspect, and this is a ratio. And when I say ratio, it means a division of two entities. And the tangent theta is the ratio of the opposite side over the adjacent side. Okay. Now, if you remember those, and right now all you need is cosine. Okay. Now, what I'm going to tell you now sounds a little silly, but this is how I heard that some students remember this. Now, maybe you've heard it before too. Some old hen caught another hen taking oats away. That's kind of silly, but it kind of makes sense. Some old hen caught another hen taking oats away. The sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Oats away. Cosine is another hen, okay? Caught another hen. So what that is telling us, the cosine of this angle is your x force, component of force, over the applied force. So let me write that down. The cosine of the angle theta in the problem we were doing before, that's a pretty ugly theta, is equal to the adjacent side, which is your F sub x. This time I think I will put F sub x. Okay. Divided by the hypotenuse, which in our problem is the applied force. And the reason I put these, you see, trig functions have to be dimensionless, no dimensions with them. And since this is a force component, that would be in newtons or pounds, and this would be in newtons or pounds, and those units would cancel out, and sure enough, this is a dimensionless quantity. So, but that's not what they gave us, okay? We know the applied force. You could put a scale on there and see how hard you were pulling on that. That's this force here. What we don't know is this component, the x component of it. So to get that, and you do know the angle here, okay? So the angle's right there. So to get the F sub x, multiply both sides by F, and that gives you that horizontal component, which is the component that's doing work. F sub x is equal to, when you multiply both sides by F, that would be F, your applied force, which you know you could measure, times the cosine of the angle that you could measure, and that angle is theta. And the cosine of a given angle is always the same. So this is what they got over. Let's see, was that on the slide set? I don't remember now. Yeah, okay. It's not written there, but this is what's written beneath that. Let me see. No, they don't do it. Okay, so what you do, since you only want this, you're given this, but you only want this, so you'd say F times the cosine of theta. That's what it is. The applied force times the cosine of theta. So now your new formula with this in mind, I'm going to have to go back to the whiteboard to write it down. With this in mind, your work is equal to, when you're pulling at an angle, but you're moving in the horizontal direction, here's the new formula. Well, let me go and type it. That'll be a little easier. I can't do a theta, but I'll write in the theta. Okay. Whoops. Okay. So your new formula for work, when you're pulling at an angle that's not in the direction, it's that force of which you pull, F, times your displacement, just like before. But now, because there's an angle in between those, you put the cosine of theta. And what I'm going to do is put an O there, and then I'll come back and put a bar in it. Is that okay? Let me draw the bar in there. In fact, I'll do a horizontal bar as close as I can get to it. Now this is going to be in black. Okay, that's my theta. Okay, so that's your new formula that we'll be using now. Work is equal to F in newtons or pounds times S in meters or feet times the cosine of theta. Cosine of theta does not have any units at all. So theta is the angle in between the applied force and the direction of the motion. Okay, so are we ready to try example 3? Okay. What I think I'm going to do is clear this off the screen. Remember this formula, okay? That's what we're going to be using. So I'll clear, well, let's see. Let me do it this way. Let me erase everything else. Okay, is that okay? Well, let's see. I think I'll leave the figure here. So maybe I'll not erase everything. We have used all this to get our formula, so we'll get rid of this. Do y'all see the little eraser, or do you just see things disappearing? And I think I will take off the opposites and hypotenuse. Okay. All right. All right. I think I'll go back to a text. Okay. A person pulls a sled along level ground a distance of 15 meters. So let's say that distance is 15 meters. Okay. Started here and moved it to here. So that displacement is here. Excuse me. Hold on just a moment. In the middle of the day, and boy, that sneeze sort of messed up my drawing here, didn't it? Boy, that's supposed to be close to horizontal. Let me see if I can. Whoops, that's not what I want to do. Let me erase that. Let me just erase all that. Okay. And then I'll get my line back, do it here. And I probably should have done an arrow here, but I'll just draw it. Oops, that's not what I want to do. Okay. I'll draw an arrow. Okay. Not a very pretty arrow, but it'll do. And this is our 15 feet. Okay. So this is our S. Oh, let me go on and put text in there. Okay. Well, where is it? There it is. S is equal to, was it 15? Yeah, no, meters, 15 meters. 15.0 meters. That means precise to the nearest tenth of a meter. There's your displacement. Okay. And it's level ground, so that's tried to get it just as level as possible by exerting a constant force of 215 newtons. Well, this is your force up here. So I think I'll go back to text here and do F is equal to, can you see that okay? Constant force of 215 meters, 215 newtons. Okay, so that's the applied force. That is in this direction. The applied force is, no, that's not what I want. I want to draw. Okay, and I want to draw a line. Okay, there's the applied force in that direction, 215 newtons. Okay, you can't do F times S. Why not? They're in different directions. But you can do F sub X, and I think I'll draw this. Actually, I could draw it with lines, couldn't I? It looks a little funny, but we could do it. There's a vertical line. Here's a horizontal line. And here's a little horizontal line. This is really what you need. I didn't need that either. Okay. Now, what we want is this component here, which is the component of force in this direction. Okay. That's the component we want, F sub X, because that's in the same direction as your displacement. Okay. So what is this component? What we said before, F times the cosine of that angle. So that means using this formula here, I think what I have to do is select now. I'll select this box. Okay. So what I'm going to do, okay, I've selected the box. How do I get it to, oh, there we go. Okay, double click, that did it. Except it wiped out my theta. Why did it do that? I don't know. That is the theta. Okay, so let's do it. The work that we're looking for is equal to, because that's the unknown, F, that's this F. It's not your F sub X, it's this F here. 215 newtons. And I'll use my time sign at X times S. Well, S is 15.0. And that will be meters, which is what it should be. And we'll multiply that times the cosine of theta. Okay. Well, theta is, oh, I didn't read for it. That theta is 30. I think I'll do a draw here. I'm afraid I won't be able to fit it without it. So let's do a draw. So this is theta is going to be 30. Point zero, and I hate this because I can't draw zeros very well. 30.0 degrees, and there's another little zero. Okay, the angle between them the 215 is at an angle of 30 degrees with the ground, 30.0 degrees. So that means three significant digits here, three here, everywhere three. Okay. How much work does she do? This is the person pulling the sled. So here, our last part here, we'll do select again. Select on this again. Okay. And this will now be times the cosine of 30 degrees. I probably should put 0.0, and then I'll have to go back to draw. Okay, and that will be 30 degrees. Okay, now I did all that so I could show you how to do this on the calculator. Now, some of you probably already know how. Let me get my calculator back again. Uh, say again. Oh my goodness, it's almost 6:30. Let's get this problem done, then we'll be through for the day. Okay, turn your phone like this so you can get to cosine. So that will be 215 times 15. You don't have to do the times zero or 0.0 times. Now, here's the issue. If you're using your phone, you have to enter the angle first and then the cosine function. If you're on a fancier calculator, you would just press the cosine and then enter the 30. So you have to know your device. I don't have a fancy calculator, I have this. And I need to be in degree mode, and I'm not. I'm in radian mode. So I'm going to change that to radian, I hope. We'll see in a minute. Okay, I'm going to multiply that by, I have to enter the 31st and then do the cosine. Now, I don't know if you can see it. You see cosines down near the bottom? Cosine right there. That's my key for cosine. Press that, and that does give me a number that's reasonable, 0.8660, blah, 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 blah. Then press equal, and that gives you the, yuck, I just lost it. I have to do it again. What was it? 215 times 15 times cosine of 30. So I have to enter my 31st, then press cosine, then press equal. Okay. Before I mess something up now, I'm going to just write the answer down. And this is equal to approximately, should put wavy lines, but I can't do that well. What did y'all get? Did anyone do it? 2,792 is what my calculator says, except there's my three digits already. So count them off, look to the right, that's a 2. We'll drop the 2 and just write a 0 instead. So 2,790, and this is in US SI units. What is a Newton times a meter? Joules, exactly. Girl's best friend, diamond, right? Okay, 2,790 joules. Let's see what they got. Oh my goodness, they got it right. So she's pulling this big old heavy thing, and she's exerting 215. Now here's the picture in the book, which is a lot better than mine. There she is pulling it. The angle's 30 degrees. The pull is 215 and but only the component of the pull parallel to the ground, horizontal to the ground, and that would be the 250 theta. And that's exactly what we got there. Okay. And that gave us that. Now, sorry that we lost so much time at the beginning. I don't know why the computer or Zoom or whoever did that. We'll pick up next time with example 4. Now, we're almost at the problem set for 8.1. If you wanted to start working on some of these, feel free to do so. I would say you can do, and here's an issue with the book. Okay, this book I don't think was proofed too well. You see a 1, and then next to that you see a 2, and then you see a blank and a 3 and a blank and a 4, right? No, a blank, a 4, and then a blank and a 5, a 6. Okay, obviously this is a right here. If I can get my finger over that, yeah, that's 3 and that's 5. They just didn't put the numbers in. Okay, so you can do any of those three, 1 through 5. Um, you could do number 7 if you'd like, and you could do number 9 if you'd like. You could do 11 if you'd like. You can hold off if you want to and not do the mower problem. So we'll leave that one alone. So those are ones you can work on. Now, hear this, folks. You've got a test now, right? I'd rather than you start sending me homework problems now, the next thing you send me should be your completed test. Okay? If you can't get it in by next Tuesday, get it in as soon as you can. But rather than you being, wait, oh, I've got to get them some problems for this week. No, get me the test. And whenever you can, if you then have a class that you don't have a test due, yeah, then you can send me some problems. But right now, all I'm looking for are your tests. Okay? So you don't have to worry about sending me any of these unless this happens. If you're trying to work some of these and you can't get the answer that's in the back of the book, you can't figure out how they got that, send that to me. And then I'll try to help you with that. We can either do it in class or we can do it in email. We can do it on through Blackboard messages. However we can do it, we'll try to do that. So only send me problems, these problems, if you're having difficulty getting the right answer. Okay. If you're getting the good answers, fantastic. Work on the test also. Don't send me anything else until you get the test to me. Does that make sense? Okay. Uh, only technically, I can't remember if she wanted you to do it every day or every week. One will do for any time unless you're having difficulty with more than one. Okay. You can turn in more if you'd like, but all I have to have to mark that you've been keeping up in class is at least one homework problem. Because it's not going to be graded, it's just to indicate you've been keeping up with the work. And now I can't put you in the grade book yet because you're in the Blackboard grade book, but I can't put you in my grade book because they're still adding people to the class. And I don't think they're adding any more to this one, but they added one to my linear algebra class today, or they're supposed to. So they added one to my uh, physical science class yesterday. Okay, so I can't do the grade book here until they stop doing that. And once they stop, then I'll be putting those marks on there. There's no way I can put those marks on Blackboard because Blackboard wants to use everything you put down. So I'll do them in my grade book, but not in Blackboard. Blackboard, you'll just have your test scores. Okay. Any other questions? All right. Have a good weekend. That's your final assignment. And of course, what will make it a good weekend is working on physics problems. That'll make it a great weekend, won't it, Manasseh? Absolutely. All right. Good deal. Any questions? All right. Then we'll see you next Tuesday. Have a good weekend. No questions. I'm going to stop the sharing. I'm not going to share anymore. Okay. And I'll end the recording. And that thing about putting the not expanding it to full screen, that didn't seem to work, but at least the block was down out of the way. So that may have helped a little bit. Bye-bye, all.